My name is Nicholas LaPlante, and I'm a third year studying biomedical engineering and neuroscience. The electroencephalogram, or EEG, evaluates brain function by measuring the electrical activity at different physical points on the skull. This project explored how EEG signals differ when participants have their eyes open versus when their eyes are closed. Specifically, I looked at how the so-called aperiodic component of the EEG changes in response to visual stimulation. For some background, electrical signals in the brain exhibit both periodic or cyclical features and aperiodic features. Periodic oscillations, which have defined frequency bands, have been studied extensively in the context of cognitive, behavioral, and disease states. The background aperiodic component, which has received far less attention in terms of research, typically follows a 1 over f-like distribution in the frequency domain, whereby power systematically decreases with increasing frequency. Also, the aperiodic signal is dynamic, changing with age, task demands, and cognitive state, and has also been linked to the relative excitation or inhibition of the underlying neuronal population. A recently created spectral parameterization algorithm makes it easy to parameterize or split up EEG signals into the periodic and aperiodic components. Image 1 shows the general idea of how aperiodic components were isolated for analysis in this project. Raw EEG data in the time domain was converted to the frequency domain by fast Fourier transform, or FFT, to generate power spectral densities, or PSDs. Then, the spectral parameterization algorithm can take the PSDs and isolate the aperiodic components from them. In image 1, the aperiodic component is shown in two forms. The left is the frequency domain version that, when summed with the periodic component, produces the full PSD. The right shows the aperiodic component in log-log space. Because of the nature of the aperiodic component, taking the logarithm of both axes produces a linear plot with a defined slope. Image 2 shows the 1020 system for EEG electrode placement. The EEG data I used came from the 9 most central electrodes in the 1020 system, that is CZ and the surrounding 8 electrodes. For each of 18 healthy participants, 3 minutes of resting state EEG with eyes open was recorded, and these are the rest open or RO sets. And then 3 minutes of resting state EEG with eyes closed was recorded, and these are the rest closed or RC sets. Moving to figure 1, the data showed a clear log-log slope shift from RC to RO, where the RO slopes were more negative than the RC slopes. Figure 2 showed that frequencies in the alpha and theta bands, which are the frequencies from 4 to 12 Hz, were very prevalent in RC sets, but were suppressed in RO sets. Expanding on figure 2, tables 1 and 2 show the average alpha and theta powers at each of the 9 electrodes used in this project. Notably, for all 9 electrodes used, the alpha power more than doubled from RO to RC, and the theta power increased substantially from RO to RC as well. It is well known that alpha activity is dominant during eyes closed resting state EEG, and this alpha activity is suppressed with visual stimulation. Importantly, this notion is supported by the results in figure 2 and tables 1 and 2. However, interestingly, the most important finding from this project is that after taking out the periodic component and examining instead only the aperiodic component of the EEG, the log-log slope shifts shown in figure 1 indicate that visual stimulation may cause an overall shift in how the brain acts in resting state. This positive slope shift has not been studied previously and could be an important point for future research, as it may provide information as to how periodic and aperiodic oscillatory activity is interrelated to support complex brain processes. Thank you for your time.